So, Vice Chancellor, sir, can you hear me? Arvind, sir, can you hear me?
Yes, now we can hear you, Shinde.
Right, sir. You can go ahead and do the screen sharing now, and you can start it up, sir.
You want everyone to do, I mean.
Yeah, I think Professor Viraj Kumar, sir, from there is where we can start.
All right. So should I?
Yes, sir. You can do the screen sharing, sir.
All right. Where is it? Thanks.
Should we be the mouse? I'll be the mouse.
No, it's okay. Okay, just a minute, please. I've got the thing open. Okay. Is this visible? Can someone?
Yes, visible. Sir, go ahead, sir.
Okay, where should I pick up from?
So actually, we lost you quite early.
Okay.
You could start it from here itself, sir.
Okay, fine. All right, so hello everyone. So I'm Viraj Kumar. I'll walk you through a little bit about computer science in general, and then a little bit about the specifics of the individual specializations. So the first thing to keep in mind is that it's really important to that computing is going to be part of every discipline, pretty much every discipline that you will imagine. So whether you are a computer scientist and then take part in some multidisciplinary team where you provide the computational capabilities, or whether you decide to major in another area, you will find that having some degree of computing in your repertoire is going to be very valuable to you. Okay, so the question about should you specialize, here is one thing I can suggest. If you would like to answer this question, ask yourself, do you know something about any of these specializations beyond just the keywords, buzzwords that we hear? If your knowledge about AI, ML, or data science is just at that level, I would say there's absolutely no reason to specialize at this point. There's going to be plenty of opportunity for you to get a very solid base and then specialize. On the other hand, if you're enthusiastic about this and you've already, for example, taken some online courses, done some projects, then definitely, I mean, you're excited about this area, definitely you should specialize, right? Now, you notice that there's a possibility here that you know something about the area, but you haven't yet done all these specializations. So there's a gray area here, and you could go either way. The most important thing I can tell you is that it doesn't really matter if you take the general program or the specialization, as long as you get your fundamentals straight. And let me just share some data with you. This report came out a couple of years ago, but the situation has unfortunately not changed very much since then. And this talks about how 80% of the people who graduate don't have their fundamentals straight. They're not employable. Right? So it's much more important. The decision is much more important that have you got yourself into an institution where your fundamentals will be clear, rather than the specialization. The specialization is something, as I said, you can decide based on your current level of interest, right? Your current level of awareness. And if you don't have it, you're not going to be at a loss. The industry is desperate, is gasping for people who have good fundamentals, right? So there are 4 supers about computing that I would like to share. You notice on this list, I only have 3, and I'll tell you the 4th in a second, because most computing programs do focus on these 3, but not on the 4th, which is very important increasingly, right? So we all know computers are super dumb. They can only do some very basic calculations, but they appear smart because they can do those calculations really fast, right? So they're super fast, but super dumb, right? Also, the cost of computing, every aspect of it, whether it is manipulating data, storing data, retrieving data, all this is increasingly cheap and becoming cheaper, right? So most computing curricula recognize all this and give you something that builds on top of these very important principles. One of the things you will have to look out for is, does your particular computing curriculum take you to the fourth super, right? Which is super specialization, right? Not so much in the data science, AI, ML, that sense, but in terms of how you harness the power of computing, because increasingly it's not just about the CPU, the traditional programming model that all institutions teach, right? But it's also about harnessing these specialized units like the GPU or application specific integrated circuits. So there are many of these that need to also be harnessed effectively if you want to use computing today, and certainly by the time you graduate, right? So if you sort of zoom ahead and ask yourself, what will I be doing after I have finished my computing discipline? Definitely you will be amongst the minority of human beings who know how to harness the power of a computer, right? Increasingly, that number of people who knows how to harness the power of a computer is growing, right? And one of the reasons it's growing is because of these general trends. Computing is now increasingly easier for people to get into. And just one example, I was recently working with some students here at DSU. We were doing an ISRO-funded project that had applications to archaeology, and the students had to develop an application. And I told them that rather than programming it in the traditional way, as you would with Android, I told them to use AppSheet. AppSheet, in case you don't know, is a way of designing beautiful and very functional mobile applications without really knowing any programming at all. And I wanted my students to be aware of the ability of more and more people to develop apps in this case, right? So the set of people who have the skills that are traditionally taught in a computing discipline, that set of people is growing. And so you have to keep yourself ahead of the curve. So as a computing professional, you can view this as an exciting thing, that your knowledge will not be static. You will constantly have to learn. And if that excites you, then this is a good discipline for you, right? And the third thing I want to talk about is, when you graduate into the computing profession, you will be part of a very large global family, right? You've all heard of open source software. As a professional, it doesn't matter if you're working for a company, you are absolutely empowered to contribute to open source software. In the process, you will learn a lot and you will achieve a lot of goodwill. Kudos is the word I have used here. And several people have managed to translate that kudos into a better job, right? There are also these open discussion forums that I'm sure you've heard of, things like Stack Overflow. And as a student, one of the things I tell my students is, contribute a good question to Stack Overflow. To be able to answer a question on Stack Overflow, you really, really need to know your stuff. But even to be able to ask a good question that has not been asked before reflects your level of understanding. It's a good check, right? So you will be part of this community. And something to keep in mind, that you're going to be graduating into this profession. This is what you will be capable of doing, and this is the world you'll be entering. Now, it may seem that this is just about programming, but I assure you it's not. There are many, many sub-disciplines of computing that get into some of the other areas. So I'll just give you some small examples, right? So from human-computer interaction, I have this lovely screenshot. This is from some work Microsoft Research did a few years ago in Bangalore and around. These are school kids interacting with a, there's going to be feedback here. So, yeah, these are school kids that are interacting with a low-cost classroom system that the teacher is running. So the teacher is asking them questions. Here's something, is the answer A, B, C, or D? And what the children are doing here is holding up giant QR codes that are printed on these pieces of paper. And depending on how they hold the piece of paper, they are answering A, B, C, or D. Right? So this is an example of research in HCI, human-computer interaction. Here's an example in scientific computing, which, because the computer could not precisely represent the number 1 over 10, 0.1. If you try and represent that in the standard way in binary, you don't get an exact value. And because of that slight error, 28 people died and 100 people were injured because a missile could not be intercepted because of that error. If you're interested, go look up the Patriot missile. And the third example I'll give is from Facebook. So my research is in theoretical computer science, and a lot of people say, "Oh God, that's so boring, so much maths, etc." But when I went to Facebook's headquarters, I got a chance to visit them in 2011. They were very interested in using algorithms of the type I was working on because they wanted to lower their energy consumption, right? And so efficiency issues are very important. This graph shows you that Facebook's energy usage is going through the roof. And this is despite the fact that they hire some very, very clever people with PhDs to try and keep these numbers down. Nevertheless, the energy usage of Facebook is quite staggering. All right, let me take you a little bit into the various specializations. So let me first talk about AI machine learning. So the overall goal is very clear to all of us. They want to mimic human intelligence. Eventually, because they're so fast, they will surpass human intelligence as long as they're able to achieve this first step, which is mimicking human intelligence. One of the earliest approaches to AI, I've used the example from the same slide that I gave you earlier, is something called expert systems, which is no longer very popular. But the basic idea is you get your expert. In this case, if you want to assume I was an expert giving you advice, I have a set of rules that I was trying to give you in this little box. And what an expert system would do is it would take the inputs and give you an output, right? Now, this is increasingly not the way most modern AI systems are built. This approach called machine learning is proved to be extremely popular. It's one of the approaches to AI. And the idea is replace the expert, the rules that the expert gives, learn those rules instead from data, right? So as part of an AI ML specialization, you will learn how to develop these kinds of models to go from data to systems that can make these kinds of predictions. But increasingly, these are not the most important skills. Again, these kinds of skills are being democratized. They are being made available to a large number of people. A good program will also tell you how to answer questions around fairness, accountability, transparency, and even ethics of should you even be developing such a system. I'll give you one example of this. This is from a news article just a few months ago, where Japan decided to fund AI technologies for matchmaking. As you know, Japan has a serious demographic problem. Their population is going down, so they wanted to fund AI matchmaking to boost birth rates. Okay? Now, from a technical perspective, there's almost no difference between that and using AI matchmaking to lower birth rates. So imagine this situation. Your government approaches you saying, we have a demographic crisis. We want to use AI matchmaking to lower birth rates. Not the government, perhaps a private agency. Should you, as a professional who knows AI, should you work on that problem? That is a question around AI ethics. And it is something that any good program will expose you to. Not just the techniques, not just here's how you do it, but should you do it? An extremely important question that is going to be more and more relevant. Certainly by the time you graduate, this is going to be front and center. Let me tell you a little bit about data science. Once again, the top level goal is quite clear. We want to improve our decision making. We have all this wonderful computation. We have lots of data. So can't we put these two together? Certainly we can. And a lot about data science is around preparing data so that you can, leverage this enormous computation to make really, really good decisions. But the key thing in data science is not really the word data, it's the word science. And I'll explain this to you with just a very simple illustration. So this is something called Simpson's paradox, which was known long before data science sort of exploded, right? But it just makes this point really well. So here's a cloud of data points in XY space. And if you just look at the entire cloud of data and you try and do just a simple linear regression, the kind of stuff you learned in school, right? You'll find that the slope is downwards. It's pointing downwards, meaning if you increase X, Y will go down, right? But in fact, the data that these points come from, this is what the colored image is showing you, is actually several subpopulations, and in each subpopulation, the regression line is going up. If you didn't know that, you would come up with this very simple model that says if you increase X, Y will go down. And you'd be dead wrong, because in every subpopulation, it's exactly the reverse. If you're interested in knowing more about this, go look up Wikipedia's Simpson's paradox. Very interesting article. Lastly, I'll talk about cybersecurity. Once again, the top level goal is we want to protect our assets from these digital attacks, and of course also recover from these attacks, right? And if this excites you, it should. It's an arms race between you and the bad guys who are also trying to defeat the current state of the art. So it can be an extremely stressful and extremely exciting domain to be working in, right? The weakest link tends to be human beings, right? And so a very important component to this, apart from the technology, are the policies to protect systems from falling foul of these attackers. And I'll just give you one quick example of this. I don't know if you are aware, on YouTube, there's someone called Jim Browning. He's probably from Northern Ireland. We don't know for sure because he keeps his identity secret. But recently he fell to a scam, right? Now, one of the things Jim Browning does is what's called ethical hacking. So he uses his knowledge of cybersecurity to figure out some of these scams. Unfortunately, many of these scams originate from our country, not all, but many of them. And what's interesting is that he himself fell to one of these scams, right? So he was convinced to delete his YouTube channel, which had millions of followers. All right, let me end with a quote. Firstly, I wish you all the best, but please remember one thing. I said this at the start, I'll reiterate it here. The set of people who graduate with the skills that industry really cares about is very small. The best thing you can do is find yourself an institution where you will learn the basics really, really well. If you do that, you will be in this very small minority of people who know their stuff and are therefore industry ready. Unfortunately, a large number of people who graduate from these disciplines are not in that position. So I wish you all the best. Thank you.
So thank you so much. You could stop the screen sharing. Yes. Thank you so much, sir.
Sure.
We would now like to move on to the next session. Our sincere apologies to all the students because of a technical glitch in the earlier platform. We had to quickly shift everybody onto the Zoom. So we are back to the original platform. And we hope we'll be able to make up for all the sessions. So thank you so much, Dr. Viraj Kumar. We would now like to move on to Professor Dr. M.S. Rajamurthy, sir. And sir would be talking about the careers in aerospace engineering. Sir, over to you, sir.
Thank you, Mr.
Sir, you can do the screen sharing.
Yeah, I will do that part.
Only the weekend. Okay.
Yes, sir, screen is visible.
Yeah. Hello, good morning, everybody. Welcome to those young aspirants who want to be engineers. In the next 15 minutes, I will just give a glimpse of what is this aerospace is all about. I'm sure all of you have seen many aircrafts. Some of you might have even flown in the aircrafts. And of course, you have been seeing a lot about the developments in space technology also. So I will just take you through the very basics just to understand what this aerospace science is and what are the possibilities that you have in it. As you can see in this slide, you can see the aircrafts. There are different shapes and they vary in terms of the capacity to carry just 2 passengers, like this small transport trainer aircraft to a big bird like Airbus A320, which can accommodate about 200 people. That's the spectrum we have. And of course, we have amazing combat aircrafts which have unique features like the Mirage 2000 here, or the A-10 bomber, or the Saab Gripen. Yeah, amazing shapes and sizes that you have in the aircrafts. Similarly, if you look at the transport aircrafts, we have transport aircrafts which carry passengers. Then we also very unique aircrafts which are designed as cargo aircrafts to carry very unique structures of the aircraft itself. Like for example, here you can see the Dreamliner carrying some components of another aircraft which is being built. So aerospace is a domain which is fairly complex. And interestingly, now we talk about aerospace science, it virtually is a confluence of all other basic sciences. Like for example, there's mechanical engineering in it, there is electrical engineering in it, there is communications, there is computing. It is just a confluence of all these basic sciences which ultimately create these amazing machines which can vary in the size and shape and weight, like a small transport trainer aircraft which is about 600 kgs to big birds like the jumbos which weigh about 300 plus tons. So that's the range of vehicles that we talk about in aeronautical engineering. And of course, in space, there are too many things that are happening here. Here is a slide where you talk about other missions called the helicopters. These are also very unique missions. So for example, or one thing that comes to our mind whenever we look at helicopters is able to hover over a position. So right now, the TVs also you have seen how they are very efficient and they do a wonderful job of rescuing people in critical situations. That all happens because helicopters have the unique ability of trying to hover at a particular place, unlike aircrafts which have to physically be moving. So this is also another great missions that comes in the aeronautical engineering. And of course, in terms of shape that what you've seen out from outside, when you rip open the aircraft is a fairly complex mission. As you can see here, there's just a cutaway of a combat aircraft, a modern fighter. You can see various things, structural things are shown, but you can see there's a radar here, there's an engine located here, there's a control surface there, there's a landing gear, there are bombs. These are amazing missions. So when you talk about aerospace engineering, you are getting into an area where you have an opportunity to be part of a team that's creating these wonderful missions. Just to give a scope that is there in aerospace engineering, here I have taken this example of our own Indian Tejas aircraft. This is a supersonic fighter indigenously developed here, but the sort of contributions that go from various disciplines, various organizations is shown in my next slide. For example, here, when it comes to building the LCA, look at the gamut of people who have participated. It's virtually a national program. Each of these specialized organizations, they have their own contributions in a particular aspect of the particular aircraft, either in terms of creating some software or in terms of analyzing some software, or in terms of creating a component, which could be a metallic component, which could be a composite component, things like that. All this goes into a program. So when you talk about any aircraft development program, it involves a gamut of disciplines, a whole spectrum of people working, from the academics to industries to small scale industries, and each one contributing in its own way to making this giant aircraft. I'm sure most of you would have seen this recent suborbital program of Virgin Galactic. One of our Indian engineers, she had participated in this particular flight. This is the Virgin Galactic, which is shown here with the White Knight carrying the spaceship 2 here, which went into the suborbital space. As you can see here, this is the Virgin Galactic spaceship. By doing this, actually what has happened is that the space programs hitherto were essentially aided by the government. Now the private players are also coming into picture. So if someone is looking at growing into an aerospace engineer, here also there are possibilities that can give you something very dramatic. So aerospace engineering, as the development in the computer science and electronics has progressed dramatically in the last 10 years. aerospace sciences have absorbed them in their things. Now we talk about computer controlled aircrafts, unmanned combat air vehicles, which are remotely operated, remotely controlled. These are all possible because of the great development in the electronic industry and the communication industry. So that has been absorbed very well. For example, if you talk about the cockpit of an aircraft, in the earlier days it used to be all dial instruments. Now they are all LCD displays. So a lot of things have happened. So in terms of aerospace engineering as a course, if you see, it has its own distinct disciplines, sub-disciplines in it. Like for example, one can talk about aerodynamics, which decides the shape of the aircraft that is required for its performance. Then aircraft structures are there. Then we have propulsion, aircraft systems. So this is something that's very dramatic. In the last 10 years, there has been great progress in power engineering, which has been absorbed very well. Now we talk about aircrafts, which use most of the systems are operated by electricity. And as I follow through, I will talk about the so-called all-electric airplane. And then control and guidance is a very important domain for these modern aircrafts, because aircrafts are becoming particularly when it comes to the combat scenario, where we talk about fighters and bombers, the future will be machines called the unmanned combat air vehicles, that is, which are remotely operated, remotely controlled, so the human life is not at risk. So these are also the development that's happening. It is all because of the great progress in control and guidance. Of course, aircrafts are very unique in the sense that they have to be as light as possible. At the same time, they should have equal strength. So the so-called strength to weight ratio that we talk about aircrafts is very important. So this material science also contributes for this in terms of developing materials which are light alloys, but at the same time, they are pretty strong. And of course, space science has its own domain that we can look into. These are all the subunits that are the substreams that come under aerospace engineering. And so when you do a course in aerospace engineering, you may become an aerodynamist, or you can become a propulsion expert, or you can think of evaluating yourself as a control and guidance engineer. These are the possibilities that one can look at in aerospace engineering. Coming to the Indian scenario itself, a lot of wonderful things are happening here. Of course, one slide I showed you before is that of the LCA Tejas. I'm sure many of you would have seen that in the Aero India program, either this year or 2 years back, you would have seen and you heard a lot about this indigenously developed supersonic combat aircraft. And then, of course, HAL has its own programs. Like, for example, there is now they're building a intermediate jet trainer aircraft. And as I was mentioning, unmanned combat air vehicles, both the DRDO, which is a defense setup, as well as HAL, they are working on some of these unmanned combat air vehicles. For example, DRDO has designed its own unmanned combat air vehicles called Ghatak. And when it comes to HAL is looking at its own combat air teaming. That means a cluster, a group of, or a small team of unmanned air vehicles can be controlled by a mother aircraft so that they can work as a force multiplier. That's what is being looked at by HAL. And then we have multi-role transport aircraft, which is also being developed by HAL. So why I'm mentioning all these things is these are programs that will run for 5 years, 10 years, because once the aircraft is built, there is a lot of testing, development, and all that. So downstream, when you take an aeronautical engineering course and come out, you have an opportunity to contribute to these programs. Maybe at the intermediate stage, maybe at advanced stage, where it's going to be refined, you are going to come with more efficient, more reliable machines. So that's what is relevant here. And then when it comes to space program, you have seen our ISRO is doing a wonderful job of launching satellites, and it is now thinking of, it is developing a relaunch use vehicle, reusable launch vehicle. So, which is essentially similar to the space shuttle, about which we have heard a lot, which has been retired from operations as of now. And then, of course, ISRO is also thinking of a manned mission programs they have got, and they've also got planetary missions and exploration programs. So, big canvas that you can look into, wherein if you do aerospace, you have the possibilities of getting into any one of these things. See, typically in an individual's career in aerospace engineering, you will get an opportunity to be part of a design development team once or twice in his career. I was happy to be involved both in the Saras, our Tejas program, that is the LCA combat aircraft. Its earlier stages, I was involved in it. And then I was involved with our own light transport aircraft, which was developed by NAL. And I was also involved in the Saras transport aircraft of NAL. So one gets a limited opportunity to be part of these developmental programs when you come out as an engineer. So it's an amazing feeling when you come out and see that an aircraft to which you have contributed in terms of design, development, whatever is flying, and that gives a great feeling. So this is what is happening. Here I've just given a pictorial representation of the various missions that I talked about. We have already seen the Tejas aircraft. Now the LCA team which worked on Tejas has come with their own new aircraft. For example, we have what's called the AMCA Advanced and Medium Combat Aircraft, which is a stealth design. The fifth generation developing, and you can see the other aircrafts. For example, here we have the unmanned air vehicle called the Rustam, and there is this sorry, there are these two, the Gatak is here, and this is what's called the Wingman, developed by HAL. So a lot of current programs that are going on in the country, which is something that's going to attract you in the sense that if you pass out after 4 years, you will see that these things are all about to fly, are going to be flying and going to be tested and things like that. So there are a lot of interesting opportunities that are possible if you get into this aerospace stream. This is again the HAL program that I was mentioning. The HAL is trying to develop its own multi-role transport aircraft, which can be used both for the civilian and military purposes. And of course, the other thing which you see below here is the HAL medium intermediate jet trainer aircraft called Sitara. So these are all the development programs that are going currently. Of course, as I mentioned earlier, the ISRO is looking for its own relaunch vehicle, so which can be used like a space shuttle, which goes in orbit, delivers the system, and then comes back, and it is reusable launch vehicle. And here, what you see is the picture of a technology demonstrator, which ISRO people tested. See, as you have heard, everyone is talking about all electric airplanes. It's a question of controlling the pollution, more efficient way of doing things. Aeronautical engineers are not behind. So already people are talking about all electric airplanes. Here is an example of a small business transport aircraft with limited seats, but the bigger players in the domain of aviation, Boeing and the Airbus, they also think of all electric airplanes. So there could be days when you have all electric airplanes which are bigger, like the transport aircraft that we have carrying people across the globe. And of course, hitherto I talked about building the aircraft, designing the aircraft and things like that, but there is an important domain called civil aviation, where we all know that the aircrafts have to carry passengers, various airlines have to operate. And here also there are a lot of opportunities for engineers. For example, when you talk about aircraft, each aircraft has to undergo a very strict regimental procedure of its maintenance, repair, and overall. This is something that is there for aircrafts, which is much more stringent than what you would think of in land vehicles, because if there's any faces when it's flying, of course, unlike the land vehicles, you can't park it in somewhere. So its performance and its reliability is very, very important. So the people in the maintenance, they are the guys, the engineers who contribute for this aspect of the airline operations. There are opportunities to become what's called the ground maintenance engineers. And similarly, there are what's called the flight operations. That means every time an aircraft flies, what happens to the aircraft, how it has performed, how it was flown, all this information is again analyzed by the flight operations group. There is a group called the flight safety group here, and then there's also flight ops engineering. You keep updating about the various aspects of the aircraft as it is being operated in terms of its engineering performance. So this is also a domain where there are opportunities that are there for aeronautical engineers. If someone is trying to pursue further after your basic degree, we have nice programs at both the Institute of Science and IITs, where you can do your master's specialization in aeronautical engineering. And of course, if someone wants to pursue research also, there are various R&D laboratories, both the government-funded laboratories as setups, wherein you can have a join and have an opportunity of doing research in aerospace engineering. So here I've listed essentially the NAL, DRDO laboratories, ISRO centers, but there are also the private players like TCS, Infosys, Wipro, Quest. They do also do a lot of developmental work that is being used for the aircraft programs. Many of these organizations have contributed to the major programs, like for example, from India, there were contributions for the, there were contributions for the Airbus A380, the giant aircraft that's flying. See, in terms of the various domains that you can think of in terms of aerospace research, a lot of work is going on in hypersonic vehicles. Then there are a lot of research that's going on in internal flows, because the fluid flow is something that's very important for the aerodynamics of both the aircraft as well as the engines that operate. So there's a lot of research that's going on in these domains. In terms of aerospace structures, people have come with lightweight structures. Now they're talking about smart structures. So a lot of artificial intelligence is built into some of these structures so that they can be lightweight, at the same time they can perform at the strength that are required. And of course, propulsion systems, there are a lot of developments that's going on, because now we're talking about hypersonic vehicles. Then avionics and control systems. This is a domain that is coming very aggressively because of the great development in both the avionics as well as the computer sciences. So then we have advanced material sciences, which is essentially focused on aerospace applications. So with this, essentially, I summarize saying that when you think of aerospace engineering, it is not just a special discipline, but it's a confluence of the various basic disciplines. So you can get into aerospace and become a control engineer, you can become a structural engineer, you can become a fluid mechanist, you can become a communication engineer, of course, related to the aircraft. And there is a lot of possibilities that are there. So one can look at aerospace as a multidisciplinary environment where you will evolve as a specialist in its own domain. Thank you, and wish you all the best. Thank you.
Thank you so much, sir.
Thank you.
Wonderful presentation. So you can stop the screen sharing. We now would like to move on, and we'd like to invite Dr. Sharat Kumar Warrier, and sir will continue about the program, the aerospace engineering program at Dayanand Sagar University. Over to you, sir.
Thank you. Good morning to all of you. And I would like to continue forward the wonderful, exciting overview of the aerospace industry today in the context of what we do in aerospace engineering at Dayanand Sagar University. As was mentioned by Dr. Rajamurthy, aerospace engineering is a highly multidisciplinary topic or a multidisciplinary subject. It's a branch of engineering focused on the design, construction, testing, and indeed the operations of both aircraft and spacecraft. So we will notice that there is always an emphasis on these two domains, aircraft as well as spacecraft, and we'll learn more about that. Aerospace is a fascinating science in that we are trying to combat or master the forces of nature and the physical properties of aircraft, rockets, and spacecraft, which is using human intelligence. So how can we use our own intelligence, creativity, innovation to deal with nature, right from going against gravity? Gravity always pulls down. How do we take off against gravity? So right from there, it's a fascinating science. There are two major overlapping disciplines. The first is aeronautical engineering, which is for vehicles that stay within the Earth's atmosphere. And the other one is astronautical engineering for vehicles that travel beyond the Earth's atmosphere. And today we have reached a junction where there is equal emphasis on research on both the areas. A lot of investment, a lot of opportunities are today being pulled into the astronautical engineering. And so we at the aerospace department are putting a lot of emphasis on acquiring the required infrastructure expertise and indeed teaching methods to cater to this very, very important and emerging area today. Coming to the contents of an aerospace engineering, if you were to choose a career, this is, as I mentioned, an upcoming and exciting field of engineering. There is a real need for innovations and discoveries. There's a lot of talk about the global warming, climate patterns are changing. So there is a possible factor that the jet fuels may be contributing to some of these climate changes. So what it means, all aerospace engineers have to be responsible and try to find alternate means of propulsion, including electric propulsion, hybrid propulsion, and so forth. So there is a real need for innovation and discoveries to be responsible with respect to the environment and the ecosystem, and of course, to take mankind's aspirations to the next level as well. Coming to the subjects per se, this is a course which requires a lot of understanding of mathematics, physics, chemistry with respect to the new materials and fuels and hydrogen cells and so forth, and indeed biology. So a lot of lessons that we learn in aerospace comes from birds and other aspects of nature. So we are trying to see if there is a parallel we can draw from millions of years of evolution in biology and how can we adapt it for aerospace engineering. So that's also an emerging area. Materials and manufacturing continues to evolve in terms of the new materials like composites and new manufacturing methods like additive manufacturing or 3D printing as it is popularly called. So there are emerging paradigms in the manufacturing as well as industry 4.0, whereby the entire production system has a lot of automation, connectivity, right from design to manufacturing. So this is the second aspect. The traditional sciences, which are hundreds of years old, fluid mechanics, thermodynamics continues to be relevant here. Structures for thousands of years, you have seen big structures, all of those principles continue to be relevant even in aerospace today. In yellow, there are some emerging areas we see in the department, which we are really focusing on is the new aerodynamics, the propulsion methods, and the design and analysis using some emerging paradigms like the digital twin, virtual twisting, and simulations. Around 10 or 20 years back, these would have been very expensive propositions. It would not be affordable to many institutes or to engineers. But today, high-speed computing, high-speed network connectivity, and low-cost computing resources and software are available. So it's creating a new space or arena for people to try out new things. The next one is on product development and systems engineering. The systems engineering part is something which will give aeronautical engineers many career opportunities. If you are having a systems thinking, your skills are portable to a lot of areas. Why it comes naturally to an aircraft engineer is once you close all the doors and the aircraft takes off, everything has to work, whether it is a cabin pressurization, whether it is a power generation, whether it is a flight and the propulsion, the thrust, communication to the ground station, all of that has to work seamlessly in flight and land safely. So this whole concept of how do you build from requirements, do the rigorous testing, get it certified, prove it is airworthy, and then take it for the life of the aircraft is taken care by systems engineering. So that's one important area. It's linked to testing and certification, of course, maintenance, repair, and overhaul, and supply chain management and aftermarket support. Post the COVID pandemic, all aircraft manufacturers are saying, how can we source parts locally in a cheaper way, in a faster way? What if the global pandemic or such situations emerge in future and we are not able to source parts easily? So the supply chain management is a new paradigm which is opening up today post the pandemic. It is, as I mentioned, and Dr. Rajamurthy mentioned, highly inter and multidisciplinary. There are 4 panels today's talk: computer science, electronics and communications, and mechanical. And indeed, aerospace engineering has to be very closely collaborating with all these departments because the developments are happening in parallel in all these areas. And at the bottom, the 2 other areas our department is focusing on is the Internet of Things, data sciences, machine learning, artificial intelligence, augmented reality, virtual and mixed reality. So these are all emerging paradigms where we are able to take pilots and the aircraft safely. Autonomous flight may come in the future. So all of these are emerging areas which is having a lot of research potential. The last but not the least there is the satellite technologies, and we also feel that's an important area for our focus. Coming to your aspects or your prospects, I would say a career in aerospace gives you job opportunities in multiple sectors of the industry. So you may choose to be in the commercial space, private industry, or in the defense sector. And you will have both industries in aircraft as well as space. The public as well as private sector is opening today. There is increasing acceptance of private players in the aerospace market, considering that around a decade or two back, it was not so. There is a research in space exploration. A lot of private players are coming into the market, and that area is going to boom. The last topic, there is the drone technologies. You would have seen even at the government level, there is a lot of encouragement, incentive, making the system streamlined, lesser paperwork, lesser bureaucracy, how to empower engineers, how to empower entrepreneurs and new players and the private players to come. So the drone technology is kind of taking new wings, if I can use the word. So that's again a very exciting area. What specifically you could choose to do? You could be a design engineer or a CAE, you could be scientist, and you could be a pilot and a spacecraft crew. Now, there is a popular misconception that you will be a pilot only in the Indian Air Force. But if you want to be in defense services, please remember that both the Army as well as Navy are having their own air operations. They have specialized aircraft. A Navy aircraft is of a very different genre compared to a normal Indian Air Force aircraft. So it is a marine technology. So you need to bear in mind that a pilot and a spacecraft need not be restricted to the Indian Air Force. There are other operators also. You could be in a drone, you could be in simulation engineers, avionics embedded, which are portable to multiple domains beyond aerospace. And of course, systems engineers and systems integrators. So these are all the skills which come to you naturally as part of your journey to become an aerospace engineer. The last part is about what are the top type of organizations we are talking of. We are talking of a lot of government and defense related organizations like the DRDO, HAL, NAL, and so forth. And of course, the private sector, right from the center of the picture on the right, where you have the operators like Airbus and Boeing's, both above and below that of the generalists, you have the tier 1 and the tier 2 suppliers of various equipment. These are all global industries which are very mature, which are highly quality oriented, highly process oriented, and use the state of the art to be the best in the market, and that is why any person who gets to work in an aerospace industry, it's a really privileged opportunities because you'll be exposed to the cutting edge technologies. Even below that, you have the airlines, the MRO, which are aftermarket, which are also extremely important part of this overall ecosystem. And at the bottom, you see there, as Dr. Rajamurthy mentioned, there are many, many new players like the SpaceX, the Northrop Grumman, and the private players, apart from, of course, NASA and other traditional research organizations, which are focusing on furthering the horizons and indeed going beyond space with respect to where aerospace technology is heading. All in all, I would like to summarize that there is a bright career in industry with a fairly good pay for the people who get to these industries. It is a very good platform for multiple masters and PhD programs, research in both domestic and international academic institutions, and a lot of startup opportunities. As I mentioned, the drone ecosystem and the materials and the manufacturing will create a lot of avenues. So with that, I would like to conclude and just say that for further information, you are welcome to reach to the department at any time. Thank you and good luck.
Thank you so much, sir. Thank you so much. A wonderful presentation to tell the students about careers in aerospace engineering. Thank you so much. So students, we have been listening to one industry panel and one from the university to give you a complete idea about how the structure of the program is, how well it is taken by the industry, and what is the industry feedback in terms of the curriculum and the outcomes. So now we move on to another interesting session. We talk about careers in mechanical engineering with the new age specializations. Mechanical engineering has also come forward, wherein there is a dual specialization available. It's a multidisciplinary program, and we're going to talk about the specializations with related to robotics and automation, additive marketing, as well as electrical and hybrid vehicles. So we'd like to invite Dr. Vinayak Hemdri, and sir will take over and talk about the programs on mechanical engineering. Over to you, sir.
Thank you, sir. Thanks a lot. I'll share the screen. Yeah.
Yes.
Is it visible?
Yes, sir.
And I'm audible also, no?
Yes, sir.
Yeah. Yeah, it is my pleasure, Mr. Sinde, for permitting me to speak and introduce my department to the audience today. I extend my warm welcome to Uniguage registered students and parents for today's webinar. And I take it as my privilege to introduce a Department of Mechanical Engineering to the students as well as parents. As we know, mechanical engineering is traditionally a conventional engineering, what you can say. It dated back before Christ, and a lot of evolution has happened. There are so many revolutions mechanical industry has seen. The latest one is the Industry 4.0. And to talk about the department, it is a vibrant department striving hard to the overall growth of the student during his stay. I'll just focus upon these two buzzwords like vibrant and overall growth. These are very, very important as far as career prospect of a student is concerned. And let us see what are the programs offered by our department. So these are all the programs offered by Department of Mechanical Engineering, a UG program in BTech in Mechanical Engineering, a PG program in Design Engineering, and we have industry tie-up, and we are running a BO course in Tool Engineering as well as pharmaceutical manufacturing also. And we also offer PhD programs also. The important thing is that I have touched upon vibrant and overall growth. What are the factors which make a student stay vibrant? Why he can feel that wow effect, what I mean to say. What is that wow effect at the end of the 4 years tenure? What is that wow effect from the student and how it leads to his overall growth? 4 years back where he is and after 4 years where he will be. That is very, very important. The first aspect that leads to this is curriculum. A curriculum, a course of study, what the student undergoes before he gets a degree. And as far as curriculum is concerned, student has to clear 160 credits, and it has been basketed or it has been grouped into different category of courses. PC stands for program core, PE professional electives, open electives, basic sciences, liberal studies, project and seminar, and engineering sciences. These are the category of courses what we are offering to the students, and how these courses are selected. That is very, very important and interesting. We have a structured BOS where eminent people from reputed institutes like IISc and IIT are the members, and they suggest, they suggest the department that these are all required to introduced into our syllabus, so that it nurtures to the overall growth of the student as far as curriculum is concerned. We take a feedback from academic requirements, industry requirement, research requirement, also from the regulatory requirements. There are regulatory bodies like UGC, NAC, NIRF, and even new education policy also dictates Department of Mechanical Engineering to select a particular category of course or a particular course for the completion of students' graduation program in mechanical engineering. Let us see what department offers as far as the specialization courses are concerned. Yeah, we can see that specialization courses, we can call it them as a professional elective courses. As I have discussed, the student has to clear 160 credits before he gets a mechanical engineering degree. In that, there are some courses which clearly are electives. So we call the electives offered by the department as professional electives. We can see here, these are all the specializations what department is offering for a student. So he has to select any one of the stream here. For example, robotic engineering, advanced manufacturing, and green energy systems, and emerging automotive technologies. So these are all the latest areas in which a lot of job opportunities are there. Student can enhance his knowledge also, and he can go for higher education also. You can see the basket of subjects with a particular stream. When he completes a particular stream of subjects, then naturally he will be awarding with a specialization certificate in that particular domain. So this is very, very important, and it enhances his job horizon. This is the main feature of the department, which helps student in getting a better job prospect. This is about specializations offered by our department. The next one, a very important and very important aspect is minor degree program. A mechanical engineering student who is pursuing his mechanical degree, apart from that, during his fourth tenure, if he completes an additional of 20 credits approximately, he will get a minor degree with other branch of engineering. This is very interesting and very important as far as widening the horizon for jobs. This is a greatest advantage what DSU is offering to its students. And next and very important aspect, as I have told you, to make students' life very vibrant and very informative, is experienced faculty members. So we are having a faculty members, they are PhD from reputed institutes like IITs, and some of them are having PDFs from abroad universities, and they have very good industry exposure. They have caliber for research and innovation to deliver to the students. So these are some of the salient features of the faculties. They can contribute to the overall nurturing of the student, overall growth of the student. Then to move forward, the other aspect which is of great importance in the overall growth of the student during his stay is state-of-the-art infrastructure and resources. This is very important. As far as Department of Mechanical Engineering is concerned, we have academic labs on all these areas. It is suffice enough to take care of all the academic requirement as far as labs are concerned. Apart from this, the very interesting to note that what is the differentiator when you compare DSU with other universities? What is that differentiator? How we can differentiate with respect to other universities? That is very important. These are all the labs available with other universities also. And how Dayanand Sagar University stands apart when we compare with other universities? That is very important. Keeping this in mind, we have innovative campus. We have Autodesk Center of Competence, Autodesk Industry. In collaboration with Autodesk, Dayanand Sagar University has established a lab on Autodesk with a suite of softwares available to students, and students are permitted to enter the lab at any time they want. They can contribute their contribution there. They can develop CAD model there. Then they can invoke that particular CAD model into a 3D printing machine, and they can develop a product of their choice. You can see some of the products what students have developed in that particular lab. You can see a tractor. That tractor is being developed. It is being a CAD model. It has been analyzed. Then it is being fabricated in a workshop itself. So I'll discuss on this more, and you can see the 3D printed models of different parts. So this is what a student can understand, how to conceive a product and how to model it, and then to how to produce it. So this is very important, and this lab plays a very important role as far as nurturing the skill set of the students. And we have Center of Competence for Automation and Automation Technologies, that is Bosch Rexroth. As you know, all the panelists and speakers spoke about automation. This is what happening in our automation lab. We have hydraulics trainer kit, we have pneumatic trainer kit. You can develop a circuitry for any complex automation system. It can be aircraft landing gear, it can be automation, closing door of a bus. It can be anything. We have a sophisticated and well-trained faculty to handle all these things. Just to move apart, I'll just make it quick. Then student specific activities. We have central cultural clubs, music, arts, and photography. Apart from this, what Department of Mechanical Engineering hosts is student collegiate clubs. And we have a very, we proudly say that the Department of Mechanical Engineering hosts a student club, collegiate club on SAE. SAE stands for Society of Automotive Engineers. It is the world-renowned body which takes of problems encountered in mobility engineering. So what does it stand for, and how does student take participation in these activities? So these are all the activities. These are all the competitions given by SAE, and our students participate in any one of these activities. So there at present, we have around 100 plus students registered for this particular student body. And we have contributed very proudly. I can say that Department of Mechanical Engineering has contributed considerable in the event called TIFAN. I'll just discuss what is this TIFAN and other things at a national level. Our contribution is very eminent here, and it is felt by the industry like John Deere and ANSYS and so many other big players are sponsors of this particular event. So what does this event consist of? You can see I have shown this tractor in before slide also. This is a onion harvester, self-propelled onion harvester. This particular tractor is being conceived This is being designed, this is being analyzed, this is being fabricated. The articulate thing is also, you can see a harvester is there, it can pick the onion from the ground and it can dump it. So you can see a conveyor, the complete set of things, starting from the conceiving and particular product to the product development. Our students have done this. It builds a confidence. Apart from this technical competence, it also develops a team building also. You can see students performing in the fields of the competition. It was held in Ahmednagar district of Maharashtra. Then we have won 20,000 cash prize for our product. These are the proud members of that particular team, Turbo Wolf. It is previous year's version, and this year also we are planning to participate in the current version of this. And apart from this, we have other students clubs on ISRE, are very promising, and around 50 students are members for this particular club. We have materials and manufacturing club. So these clubs help student to grow, and it leads to overall growth of a student, which nurtures for improves his technical skills, it improves his communication skills, it improves his team working capabilities. So these are all the important aspects, and ultimately it leads to overall growth of the student. And apart from this, the recruiters, this is very important. And at present, when he completes, these are the what I can say, program specific outcomes. When a student completes his 4 years degree, he can be a design engineer, he can be a production engineer, he can be a maintenance engineer, he can enter in planning, and he can go for technical sales and marketing. So the job prospect or job horizon is wide open. Be prepared. These are the specific outcomes what students should get once he completes the degree. And these are our recruiters, very renowned companies like Continental, Plus Globe, Toyota, Tegutech. Yesterday only one of my best students has been selected in Tegutech. Is one of the leading manufacturers of cutting tool. Pot Toolings, DHL Supply, and these are all the companies, firms where our students are being recruited with very good pay. And this is how the Department of Mechanical Engineering nurtures, or it caters to the overall growth of the student, and it helps them in building their careers, not only in industry as well as in public sectors, as well as in government jobs, as well as to undergo a higher degree. With this, Department of Mechanical Engineering strives for quality and excellence. It cares for students. With this, I'll conclude my talk. Thank you for providing me this opportunity so that I can introduce my department to the people. Thank you, sir. Thanks a lot.
So thank you. Thanks a lot. We'll just stop the screen sharing. And we would now like to invite Professor Ravichandran KS. He is a former senior scientist at National Aerospace Laboratories. He's also an adjunct faculty at Dayanand Sagar University, and he would be giving the industry perspective towards the new age specializations with mechanical engineering. Over to you, sir.
Okay, thank you very much. And I hope you are able to see my screen here. I don't know.
So you'll have to do the screen sharing.
Let me just check that. Screen share. Start video. Share the screen. Share. Then you're able to see my PowerPoint presentation here
yes,
now?
Sir. Please go ahead, sir.
Okay, so my name is Ravichandran, and at the outset, let me thank Dr. Hemadri for inviting me to make this little presentation on what are the applications of machine learning of late in the area of primarily we are talking about numerical simulations in mechanical engineering, basically in terms of computer-aided engineering and computational fluid dynamics. And of late, we have some applications of machine learning coming into these areas. And I will touch upon a couple of applications of machine learning in these areas very briefly and just give you a small glimpse. So what is technology all about? So we basically, in terms of talking in terms of machine equipment, we are talking about various gadgets and artifacts in all aspects of engineering. So we could be talking in terms of transport equipment, ships, rockets, planes, etc., or might be talking about automotives, or might be also talking about things in terms of highways, dams, buildings, applications of civil engineering. There are also mechanical machines, lathes, drills, etc. And then if you come to modern technology, then we are talking in terms of computers and tablets and microchips, etc. So this is all about technology. Now, engineering, in my mind, is all about development of these tools or equipment and other engineering devices. And then, of course, we have to talk in terms of performance of these devices. And then we also have to say a few things about the life cycle of these devices, because the consumers are generally more concerned about the life cycle of these devices and the performance of these devices, their reliability, etc. So when we talk about classical engineering, it's all about using classical tools. When I talk about classical tools, I basically have in mind, for example, numerical simulations. So we talk in terms of classical tools, which are for application of structural design, or for thermal or fluid dynamical design. So some of you might be aware in terms of some very popular tools in these areas. One of the most popular tools is ANSYS. And then we also have, for example, fluid dynamical applications. There are other commercial tools which are available, which go by the name of STAR CCM, etc. And then we have NASTRA and other things for computer aided engineering for structural design, vibration analysis, and things like that. So when we are talking about these classical engineering tools, they are, of course, surely used for analysis of given design, and they are able to estimate what kind of performance they are likely to be guaranteed, and how they can be developed, and also give you some idea about the life cycle assessment of these devices. But largely what happens is, when you use these devices, at least till about 10 years back, we were generating a lot of legacy data, and hardly ever look back at the legacy data as to how it can be used for future design. So what's happening over the last 10 years or 15 years, I can say, is that machine learning has come of age. And primarily, as has been described by all other people, especially by the first speaker, that machine learning has been considerably aided in terms of the development in computing power. So machine learning aided engineering, now we start looking at legacy data, and we have plenty of it, and we ask the question as to how this legacy data can be used for current and future design, not only for design but also in terms of performance assessment, and also life cycle estimations, etc. So machine learning uses not only current data, but also it learns from the data. This is one of the things that was emphasized by the first speaker, that machine learning is, as the name itself suggests, is something that not only can use the data in order to produce a certain output, but also use the data that is thus generated in terms of learning new rules from this data, and then coming up with its own self-modification to make further predictions. So, so what are we looking at? The machine learning paradigm is something that that can go beyond what the engineers can visualize in terms of the design possibilities, but also develop some rules in order to modify their own behavior, and thereby come up with new designs that otherwise they may not have been able to intuit or discern. So wherever we have lots of data, it is open for us to apply machine learning techniques. So what is the workflow process in a machine learning system. So this is largely this, what you see here is a very simple schematic of what a machine learning system is. And it is quite irrespective of, which discipline that you're applying it to. So you can see here that the inner system consists of a data set. And then within this data set system, you have an input data. And this input data goes into a system about which you know very little. But this system is using these input data, processes all the input data in order to come up with an outcome. And this is the outcome which is basically we are interested in. So if you're talking about, let's say, simple compressor, then compressor, you have the geometry input. Then you might have some user control input, like, the RPM of the compressor, the actual design of the compressor, number of blades in the compressor, how many stages are in the compressor, and things like that. So all this constitute the input data. And the physics of the compressor actually is captured by the system parameters that we are talking about. So once this input data is specified, some of which is controlled by the user, others are somewhat fixed to the system under consideration. Then this data is taken in by the system, and then the physics of the system under consideration actually comes up with an outcome, and which basically what we talk about in terms of performance parameters. It could be efficiency, or it could be the the compression achieved and things like that, or what is the flow rate. So these are the things which are actually interested in. So we are basically have a paradigm where we have input data, there are system parameters, and there is an outcome. So where does machine learning come into the picture here? Classically, we have been working only with these three things. All tools that I have talked about earlier, numerical simulation tools that we are talking about earlier, they used to take this input data, then have a way of representing the system, and then they can process all this input data and then come up with the performance parameters that we are interested in. Now, given that you have, let us say, 100 such designs, and you have generated corresponding to each design, a complete table of all the performance parameters, together with all the input data that goes for each of those designs, then we have this huge data set which is available to us. Now, the question that we are going to ask is, how are we going to use this legacy data that we have generated? How are we going to use this for future designs? And that is where the ML algorithms actually come into the picture. So this entire data set, which in machine learning terminology we call the training data set, gives the machine learning algorithm an overview of what system that it is dealing with. And the machine learning algorithm is capable of actually capturing the behavioral aspects of this data set without knowing what actually it is dealing with. So that is the key thing. That is why this machine learning entire paradigm makes it very, very general. And so you don't really need to know what exactly is the data set. So the machine learning algorithm takes this entire mass of data that is made available to it. It is able to capture the system characteristics, and then once it's able to capture the system characteristics, we have what is called a model. So this model now is available for us for this particular system. Now, when this model, once it is frozen for this particular system with the given data, then we can give new input data to it. And that is where it goes back into the new input data. Once it goes back into new input data, you can skip this intermediate, input data, which is processed by the traditional tools. You go now, you take this input data, you bypass this entire intermediate stage, and then say that because I know the system characteristics, I can take this new input data, which is in terms of, let us say, I want to, alter some of these parameters, input parameters, in order to come up with a new design. And this new design can come out as an outcome now. Okay, so now this new design which comes out as an outcome, it should be possible for me again to go back to the traditional system to see, because the traditional system has all the physics, and see whether it is going to meet my expectations in terms of the engineering design. So that is what the simple machine learning work cycle is all about. So now we are going to take a look at an application of this idea to two very specific examples. One applied to computational computer-aided engineering, the other one applied to computational fluid dynamics. So the first one is about a CAE application. The idea here is we have a vehicle here, and there we have a bumper here, the front bumper, and we are going to talk about analysis of a crash simulation, which is generally a regulatory requirement for all complete vehicle design. So we are talking about a crash simulation of the front bumper. So the idea is we need to propose a process change for the analysis of the crash simulation results. So what is it that you can do actually? We have traditional tools which are available for crash analysis. So we can use LS-DYNA or any of these nonlinear analysis tools in order to generate results in terms of the strain that is results from a particular crash phenomenon that you are going to simulate. So you can use any of the traditional tools. ANSYS also you can use, or you might use Abacus or any of these tools. And then having analyzed this, done this analysis, the idea is that how do we, we have of course some parameters which go into the design of this bumper, and we want to generate a huge data set in terms of variation of these parameters, and then we have to process the results. So what does this entire exercise consist of? You have we have two technologies basically in terms of machine learning application. We have dimensionality reduction and then rule mining. The idea of rule mining is that we have a lot of data, generated data, which is coming out of the analysis, but we need to know what is the causal relationship between the effect that we are looking at and the causes, which is basically that of crash, and the parameters that actually define the crash. And then we need to understand what is the causal relationship between the initial cause and the ultimate effect. So the crash model is a bumper of 2007 Chevrolet Silverado, and we have three physical parameters. One is sheet thickness, which is the thickness of this bumper, and of course we vary the impact yaw angle, and then of course we also vary the velocity. So there are basically three physical parameters which are involved in this design of this bumper, and setting limits for certain ranges for each of these parameters. We are going to do 1,000 simulations and generate 1,000 sets of data. So what does this 1,000 sets of data actually mean? This 1,000 sets of data basically in terms of the normal strain which is induced in the bumper in each of those crash operating conditions. So then, since you have 1,000 sets of data, and you know that this bumper is actually divided into any number of large number of elements, 100,000 elements or 200,000 elements, then associated with each of the elements, we have plenty of strain data which is available. And then that means 1,000 simulations with 100,000 strain elements plus 3 strain parameters which are associated with each element. We have 100,000 into 1,000 into 3. So we have that many number of performance parameters, if you want to call it that way, that are available for us to analyze. Now, how do we now, deal with this huge amount of data? And that is where the dimensionality reduction comes into play. So we use a certain process, which I'm not going to details here, but what we basically do is we use the dimensionality reduction as a technique in order to reduce this huge amount of data into 2 or 3 major buckling modes, okay? So we want to reduce this huge amount of data into 2 or 3 buckling modes. And then once we have identified the buckling modes, we want to do a little bit of rule mining, which is basically the exercise to discover the cause-effect relationship between the buckling modes and the original causes, which have to be contained within these 3 parameters that we started with. So now we go to the, so I'm talking about buckling modes here. These buckling modes basically consist of, now we have already done the dimensionality reduction, and you see that here that, you know, there are 3 axes here. One is the strain, normal strain in the X direction, normal strain in the Y direction, and normal strain in the Z direction. So these 3 parameters available. So in the strain space, we put each one of these outcomes, which if you remember that we have 1000 of them, which have been further reduced, and then we have reduced them to roughly 1000 data points here. And these data points here, we use what is called the clustering as application of machine learning technique. And then we separate them into these 3 different groups that you can see here. So these 3 different groups tell us that one is, there is a dent to the left, one is dent in the middle, and then there is a dent in the right side. So these 3 very nicely separate into these 3 groups because of the machine learning clustering algorithm. And now we are able to identify that given these 3 modes of deformation that we have as a result of our analysis, the question that we are going to ask is, what causes each of these deformation modes? So the question is now, the idea, the question is to discover the causal relationship between the deformation modes and the input parameters. And we go to the next slide here now. So we go to the next slide here now. So once again, you have the thickness. If you started with the thickness and the yaw angle as the power 2 parameters of 3 parameters that I talked about, velocity is not mentioned here. So you have thickness here, you have yaw here, and you have 1000 points which are plotted here, which are the outcome of the analysis. Now you want to know, to start with, of course, you would have had all this, cluster of points which are appearing on this graph here. Now the question that we are going to ask is, what is the range of these parameters, each of these parameters, within which each of these deformation modes actually occur? So if you look at this, now there are 3 colors that you can see here: blue, green, and the gray. And we are asking the question, mid-denting as a deformation mode, what is the cause of mid-denting mode? So the machine learning algorithm, which is in this particular case is called the decision tree algorithm. Again, the details of which I'm not going to here. But if you give this data, cluster of data, to the decision tree algorithm, then the decision tree algorithm will come up with this segregation of the data into these, first of all, these colors. And then subsequently, it will also tell you what is the range of yaw angle and the bumper thickness, that is thickness of the bumper over which this mid-denting is actually occurring. So you can see here that this is the yaw angle range over which, and the entire bumper thickness range, you have, of course, mid-denting happening. But there is also another cluster here on the top, where the thickness of the bumper is between a slightly lower value, but it goes right till the upper limit, and also the yaw angle over the upper limit of the yaw angle range. So over this, you also have again the mid-denting deformation possible. So this is an example of an application of machine learning for CAE analysis. And a similar thing that we do is for computational fluid dynamic analysis. This example that I'm going to cite is going to be very, very simple. Normally, we know that we generally the objective of computational fluid dynamics is to solve a set of differential equations, and we have commercial tools which are available for that. So you given any geometry and you specify, some flow parameters, angle of attack, flow velocity, or all other temperature or pressure and things like that in free stream conditions, and then you define the geometry, and then you do a typical meshing and carry out an analysis. You'll be able to come up with a flow field. So that is the That is what a computational fluid and dynamical analysis is all about. And many commercial tools are available. As I mentioned, the ANSYS Fluent is something that you can typically use for this kind of calculation. But the key thing about this kind of calculation is that if you are going to apply this for an entire aircraft, then it can take, even today in today's technology, ANSYS Fluent can take maybe a couple of 2 or 3 days in order to be able to come up with solution for one specified operating condition. So it's a lot of computational effort. Now the question is whether it is that I have analyzed plenty of aircraft geometries and I have accumulated a lot of data relating to different geometries, different operating conditions, and therefore again I have a huge data bank. The question is, can I use that in order to be able to come up with analysis for a new geometry? So that is where this kind of an application, but here I'm going to illustrate that using this very simple geometry where you see a blunt body, facing a free stream flow. So here I'm going to use this artificial neural network, which is abbreviated as ANN, and we want to predict the fluid flow. So if you want to, given the shape of the object, as you can see here, shape of the object, and also what is the oncoming flow velocity. Of course, the oncoming flow velocity is shown to be very parallel to the axis of the object here, but then it could be, something different. But I'm not getting into those things. So if you are going to look at, if you are going to ask the question, given this kind of a shape and your flow parameter, which velocity, which is coming with 0 angle of attack on this object, and I have a whole range of velocities defined and generate a lot of data, is it possible for me to use that entire data set to come up with artificial neural network system, which given a new geometry of the same shape but different velocity, then can it predict the flow field? So here the parameters are input parameter, you might say, is the center of curvature here, then the leading edge radius, and then you have, of course, the length of the object, and then the width of the object, and also you'll have to define the free stream flow velocity and the angle of attack. And the output will be the flow field, u velocity, v velocity, and the pressure. So what do we do? So we vary these parameters. As we did in the previous case, in the CAE case, we vary these parameters and we generate a huge data set, let us say, and that will constitute what is called the training set for the machine learning algorithm. So once you have that kind of a machine learning algorithm, and I've already shown you the workflow for the machine learning algorithm in the earlier case, and then you give this entire data set to the machine learning algorithm, then the machine learning algorithm knows what are the characteristics of this system where an object is, facing an oncoming flow, and it can output the pressure, velocity field for the, for any given specified parameters. So here on the left side, you have a CFD analyzed flow field that you can see here, where I think I have plotted the velocity of the velocity field of the entire flow, and the machine learning algorithm has been given about 300 number of such simulations, and from the 300 number of such simulations, it has learned what the characteristics of the system are, and then now I give another velocity, and in this case I have kept the width and the geometry shape more or less the same, but I given a different velocity, and ask the machine learning algorithm to tell me what the flow field is like, and I have again plotted the velocity field here, and you can see that the velocity field predicted by the machine learning algorithm and the velocity field actually analyzed by the CFD algorithm are more or less the same. So this is essentially the kind of things that we have been doing of late, and these things we are not doing earlier, about 5 years back, but it has become commonplace now. And I expect that most of our tools for CAE analysis and computational fluid dynamic analysis will now have the capability so that the user can generate a lot of data and should be able to invoke a machine learning algorithm from within the tool and then you be able to do an analysis based on the data that is already generated for new configurations. So thank you.
Thank you so much, sir.
Yeah.
We would now like to move on to the last session of the day, where we have careers in electronics and communication engineering. And the best part of it is it comes with the new age specializations on automotive electronics, embedded system design, and IoT, VLSI design, and signal processing. Mr. Rajan, sir, can you just stop the screen sharing?
Yeah.
I would now like to invite Mr. Pankaj Bande. He is the Chief Technology Officer at Wiz Club and the former Senior Architect for IoT Solutions Engineer at Wipro. Over to you, Mr. Pankaj.
Thank you. Is my voice audible?
Yes, sir.
Okay, thank you. For a moment, I will just show my face so that people get to know that there is no alien on this side. And
there's a light behind you, which is slightly shining more. There's a light behind you.
Yeah, so I will just stop. We can focus on the part which I wanted to show. Yeah, so quickly, I just wanted to take you through, since I represent Wiz Club as a company, I just wanted to show you a quick video of what we do and how all of you who are part of this session, means every engineer, because I represent the company side, how every engineer actually, is part and parcel of what I do in Wiz Club as a company. So there is this small video which actually explains how the electronics engineers, how the computer science engineer, how the mechanical engineers, and even people who are specialized into VFX and all of that, all of them work together, and we actually do an event. And this event is an event wherein 1 million line of code is executed by 10,000 people sitting across the world. Okay, so what is that setup? How these engineers come together and they work for me. And the same setup or the same opportunity is what you get during your engineering, because all branches are there, such knowledgeable professors are there, industry partnerships are there. But how does the industry consume the talent, right? So what we do here is that I'm just trying to show you a breadboarded version of the world's first ambient computing cloud IoT lab setup. So you see a lot of things, right? A breadboard is electronic, plug and play kind of experiment setup. But then how all of these come together, a lot of electronic components, processors and all that actually are brought together, and we actually make a cloud IoT lab, right? And it is very much in Bangalore, HSR layout, where our office is. So I will just try to show you that, okay, we start with simple capacitors, then there are wires, we see some ultrasonic sensors, we see some OLED displays, and then there are these ESP32 processors, which are microcontrollers, and most importantly, the breadboards on which all of these things are supposed to come together. Now, here are the two most important electronics engineers. So I have Avinash and I have Divya, who are part of my electronics engineering team. And they have a solid skill set of, understanding entire electronics engineering and breadboarding circuits. And they are helping me to create these circuits on breadboard. And they are trying to put more than 10,000 components in this world's first IoT lab, right? So that's where the electronics engineers are coming together. And while they are doing this, I have Ajib, who is a mechanical engineer. And what he is doing is that if that setup has to be created as the world's biggest setup, he is designing the CAD part of it in Fusion as a software. So I have the mechanical engineer with me as a part of the thing, and he's using Fusion as a software to design the setup. And then, I have another mechanical engineer who is part of the team. I will just play and we will be able to see him. So we do laser cut that setup now, which is designed in Fusion. And yeah, here is Amar, who is a mechanical engineer, who is now trying to complete the assembly of this setup. So what is happening is now this setup is coming up, and the laser cut part of the wood and the metal part come together. And these two mechanical engineers are now trying to complete the setup over here. Now comes the electronics engineer, Divya and Avinash, and they are trying to position all the 10,000 components on breadboard here actually. So you can see that, they are positioning these breadboards, and this is becoming a huge setup of, electronic components being positioned on a mechanically designed setup actually. So this is how it looks. So I'll just play it for a while. So this is how the entire setup has come through. So you can see the combination of, the electronics engineers core skill set, and the processors, the sensors, the servo motors, RGB LED strips, capacitors, power supply, everything is coming together, and the mechanical engineering team members did this thing, and now this is there. Now this is the computer science engineering guys. So this is an online website which is designed by the computer science engineering team in my company. And what they did is, now they connected this website to all the hardware which you see here. The hardware which you see here is now connected to this website. You can read, right, offline, online, these words. So whatever we are able to now actually see in the electronics and mechanical domain is now seamlessly connected to the computer science world. So here we are, these devices are all IoT, and this is how, once they are online, this is how beautiful they look like. They're all there actually, and they're all working together, and this is world's biggest, breadboard version IoT lab. And that's where the computer science engineer, the mechanical engineer, and the electronics engineer worked for me together. Now I'm showing you another world's biggest version of the PCB designing version of that. So now again, PCB designing falls into electronics engineering. So okay, there are labs, there are engineers who have done this PCB designing using Autodesk Eagle software, and this is the initial level of the setup wherein a larger team is coming into picture. So these are some of the glimpses which I'm trying to showcase, that how we work as a team together and bring it. Again, Ajib is designing, now he's using SolidWorks as a software to design the setup part of it. So he's now creating, and then Amar is getting the 3D printing, the laser cutting part done for that setup for the PCB designing version. Now Sandeep and Ajib, Sandeep is a mechatronics engineer, so he and Ajib is now trying to complete the mechanical part. And now because Sandeep is a mechatronics guy, so he helped in mechanical, and now he's also playing the role of a electronics part because he's a mechatronics specialist. And this is how the setup looks like. The larger team is having all these things, and these devices are connected across to anything in the world, whether it is a cricket match, whether it is Olympics, whatever you want. This setup is IoT setup, and it's world's only lab. It is only available in India in our setup basically, and all the engineers are working here. So now these are the 10,000 kids across the world, the behind the scene, who are now going to be a part of a world's biggest event of 1 million line of code, and it is getting into India Book of Records also. And I'm saying kids, I'm saying you are all 12th graders, right? So from 3rd grader to 12th grader, all the kids are part of this event, and how they are programming it and triggering 1 million line of code together. So this is where again programming comes into picture. So now they actually send the data from here to the satellite, then it goes to our server in North Virginia, then our IoT server in Dublin, either via satellite or sea cable. That is what I was trying to show here, that this lab is now connected to our server in North Virginia, either via sea cable or satellite, and it is connected to all the locations in the world, and the setup is in Bangalore. Okay. Okay, so these are some of the example kids who have done the initial testing, and now they are going to program these devices. So a simple programming language is Blockly. Now they are trying to do Alexa skills, so they can talk to these devices because it's an ambient computing lab. So if we have to understand what is ambient computing, anything can be done just by talking. So now you are talking to this India flag on the breadboarded version. So you say, hey, I want this flag to move, talk to Alexa. So the child has done a programming in Alexa here. So this program now talks on the Echo Dot device, and this flag moves. So if one can move, can hundreds of these flags in the IoT lab move? You can see it now. So these kids are now programming it, and this is all working. So can you create a chatbot for this? Yes, you can program a chatbot in the computer science domain and connect. Can you program it in Python? Yes, you can program this lab in Python, and you can actually see the devices working. Can you design HTML, CSS, JavaScript web apps? Yes, it is possible for you to create web apps and connect to these devices actually. So, these are the things. And then we have also heard about, machine learning. So this is IoT machine learning. So I do a sentiment. Am I happy? Am I sad? And based on that, my sentiment is printed on that lab device. So this is all interconnected. And when you do engineering, you pick any branch, but you must collaborate with other branches and work on it. So this is where I'm now trying to show you the tech stack. What are the technologies which are used behind the scene? Okay, so I will just make this run. Yeah, and then I'm holding it here. So if you now look at it, it has got a lot of cloud components. You can see Adobe tools here. You can see Microsoft Visual Studio Code. You can see, the processor is here. You can see SolidWorks Fusion 360. You can see, the things like Zoom and Google Meet, Google Analytics and Facebook, and then machine learning components. And then the Arduino is there. Some of you might have worked on Arduino and all that. So all of this comes together to create a lab, which I was just trying to show you. And all of this requires every branch of engineering to come together. And while I'm supposed to give you the idea of the electronics part of it, because I have a bachelor's and a master's in electronics, but because I am a CTO of this company, I can't stop. I'm still learning. I learn from the mechanical engineers, how they do. I learn from the computer science engineer, how they program. And I contribute as an electronics specialist in the electronics engineering domain. So that is what is the case, right? That Virat Kohli is a batsman, but he is also a captain. So he's an individual contributor as a batsman, but as a captain, he has to work well with all the team players, know who is the best bowler for which situation and all that. So that's the kind of expectations, if you have to ask me, because I represent industry, if you are becoming an engineer, pick any branch, pick electronics, be good in electronics. So you will become an individual contributor in electronics. But you have to be good in understanding other branches, like the cloud components from computer science. You will see security aspects of it, which is a cyber security specialization, which DSU offers. Or you can be a CAD design engineer with Fusion 360 and SolidWorks tool expertise. But you can't run away, right? You have to work with the electronics guy and you understand the electronics of it. So you keep learning, and that is what is the case over here. So I just take you through. This is just the tech stack and then the architecture, how all of this connects together, and you are able to see so many things basically being interconnected. So this is where, and I'm not saying you will be able to do. So now these are the 2,859 files which combine together 20 programming languages, and it actually runs 8,83,694 lines of code actually. So how does this look like? So the code look like this, that what are the files, how many lines are there, and these are the number of files which our computer science engineers have done. And this is how the overall setup responds to that. So it's a combination of everything which you tend to do. But if you pick electronics, be very, very good in, electronics. If you pick mechanical, do that. But when you come to industry, and we have heard it in the aerospace also, it's multidisciplinary. Whether you go to, any of the case, we saw such a detailed analysis of a crash, if a car crashes, how the machine learning, the computational fluid dynamics and all of that come together. But that's what, when you will pick Dayanand Sagar University, ensure that you work in your domain, learn from the best of the professors, your own branch, but collaborate with other branches, students and professors, and be part of such events actually, so that you actually end up as a complete personality, wherein you remain an individual contributor of your branch and you also become a overall person. That's what, if you ask me, if you want to recruit me, I pay a 12 lakh rupees package for an engineer who works for me. I am not going to take someone who doesn't know the overall thing and also specialized into a specific branch of his own. And that's how it works for me as a person from a company. Okay. So that's it from my side. This is what I wanted to share as an experience, and thank you, Vice Chancellor sir and Shinde sir, for giving me this opportunity to present my domain here. Thank you so much.
Thank you so much, Mr. Pankaj. Good to see a true practical exposure and the amount of work and the quantum that the students can do in the field related to electronics and communication engineering. I would now like to invite Dr. Vaibhav Meshram, the professor and chairman for the electronics and communication engineering stream. Over to you, sir.
Thank you, Mr. Shinde, sir. Thank you. Am I audible?
Yes, sir.
Let me share my slide. Give me a minute, sir. I'm sharing my slide.
Yes, sir.
There is some problem. Give me one moment. So my slides are visible.
Not yet, sir.
I'm not able to share. Shinde, sir, can you share my slides? There's some problem here. I emailed you the slides.
Right, sir. 1 second. I'll just have it
Yeah, please, please.
on the screen. Sure. Just give me a second, sir. I'll put it across.
Sure, sure. So I welcome all my dear students and the panel members to this presentation. I'm Dr.
Yes,
Vaibhav.
sir.
Yeah, thank you very much, sir. To put it in a slide show mode.
Yeah.
Yeah, thank you so much. I'm Dr. Vaibhav. I had done my BTech from REC Kurukshetra and MTech from IIT Mumbai and PhD from BITS Pilani. I had worked around 15 years in the industry. After that, I switched on to the academics. So my dear students, I feel that electronics and communication engineer is a hardware come software engineer. He is not totally a hardware engineer. He is not totally a software engineer, but the hardware plus a software engineer. Whenever I will say my electronics to engineering student, I will say that you are electronics come software engineer. So next slide, please. So let us see what is electronics. So electronics, sir, can you move to the next slide? Electronics is a. So let us see what is electronics. So electronics is an art of controlling the movement of electron in order to design a component and circuit. Circuit may be your laptop, circuit may be your mobile phone, circuit may be your TV, circuit may be your FM radio. But this circuit in itself is of no use if it is not communicating with other. If I have a mobile phone and if it is not communicating with other mobile phone, then what is the use of that circuit, that mobile? If I have a TV and if this TV is not able to communicate, if I'm not able to see the Tokyo Olympics on my TV, it's of no use. So the another aspect in the electronics engineering is a communication. The devices or the circuits or the equipment should communicate with each other. So this is the electronics and communication engineering. To make this happen, so next slide. To make this happen, we need appropriate hardware to make this work, the circuit and this we need appropriate software to make this circuit and this communication to work. Not only we need appropriate software, but we want this circuits as well as this communication to work intelligently. So we had added artificial intelligence and machine learning to the components and to the circuits as well as on the hardware side. So AI and machine learning in electronics and communication is introduced in various subjects like VLSI design, in a signal processing and all this thing. Apart from this thing, the Industry 4.0 revolution is driven totally by electronics and computing, electronics and communication. So next slide. Is driven totally by electronics and communication engineering. To make this happen, we need a trained engineers in the electronics and communication engineering domain. So for this, next slide, sir. For this, we need facilities and faculty. We need facilities and faculty. So we have the state-of-the-art lab in our Dayananda Sagar University, a School of Engineering, Electronics and Communication Engineering department, and we have a well-trained faculties, those who are quite experienced. There are around 60% faculties in our department are PhD, and some of them had done a PhD from abroad. So this will help student to develop, and this will make student to be ready for the Industry 4.0 revolution, and in the domains like communication, signal processing, embedded system, and IoT. Next slide, sir. So we have the lab facilities related to the communication engineering. For the communication engineering, we have a lab facilities from Mentor Graphics, and for embedded system, we have a lot of lab facilities. These are the industry-supported lab from Bosch ITAS. For the signal processing, we have analog devices. We have a lab from the analog devices. Apart from this, we have analog circuits lab. This will train students into the domains. Facilities plus faculties plus mini project from third semester onwards will lead us to industry-ready engineers, those who are hardware come software engineers. Apart from this thing, these facilities, faculties, and the project from third semester had created some magics. That magic is that students are doing a project. Students are doing the projects which they will be demonstrating in their final year. It is not in our department, in our university, that students have to do a project in the final year. But we will start training students in the domains from third semester itself. So they can do some projects which are industry ready. So we will have a project exhibition every year. We will have a project exhibition every year in the department where we will call the people where we call the experts from the industry. And believe me, the expert from the industry had commented that if little bit tinkering is done, this project are product ready. These projects are can be developed as a product. So total 38 projects were demonstrated by the student, and it was a very tough time for a panel member to select which one is the best. Even though they had selected the best project, and these were the best for 4 projects: assisting health worker, image analysis, multimedia parameter, unmanned aerial vehicle. And our 8th semester student had find the patent for their project. So if you go to the industry, my dear student, if you go to the industry and if you said I had done this project, I have expertise in this particular domain of signal processing or embedded system or VLSI, the industry will be ready to hire you. And if you say moreover that I had also find patent for my project, then there is nothing. That is icing on the cake. So always be there will be icing on the cake. So going ahead, what is the future and the job market? The future and the job market. If you take any domain, if you take any devices, if you take any device or a gadget that you are coming across, you can be improvised using the electronics. So this is an ample amount of the job market. Ample amount of the job market is there from, you can say, public sector, MNCs, entrepreneurship. You can become an entrepreneur. You can become a good researcher. And in fact, when you are going to pursue an MTech, they will ask you, if you are going to pursue an MTech in abroad universities, they will ask you what was your project. And if you tell that I have a domain expertise and I had done this project, you will be definitely taken for the postgraduate studies. Definitely, industry will also like to hire people who are hands-on. So in our department, facilities plus faculties plus the emphasis on a project from third semester onwards leads to an hands-on engineer, which are electronics, which leads to an hardware engineer, which are electronic, which are a hardware plus software engineer. So having said that, I will conclude my presentation here by saying that we create an intelligence in silicon. My mobile number is 7259108645, and you can log in, you can call me anytime, or you can write me anytime. I will be more than happy to help. Thank you, my dear students, and thank you for giving me an opportunity for presenting my department, my EC department to the student. I will love to see you, my dear students. I will love to see you in our DSU portal, and I will love to see you using our facilities. By using our facilities, you can become you can make a good project. You can also find the patent. Thank you. Thank you. Thank you, Shinde sir.
Thank you so much, sir.
Thank you. And sorry for the inconvenience because I was not able to share my slides because of some technical problem here and there was some login problem. Thank you. Sorry for it.
Thank you so much, sir.
Thank you very much.
With this, we come to the end of the entire session today. I would like to thank all the students. We are extremely sorry, we'd like to apologize with everybody on the major glitch that happened on the web, on the Uniguage platform. There are a lot of restrictions on the platform, because of which we have various speakers from different part of the country, and they could not log in, they could not use the particular platform to the extent, and we had to shift everything to the Zoom platform. So we are extremely sorry for this, but yes, we are coming up with another very, very important and an amazing session with all of you in the first week of August. We will communicate the dates and the time to you, and we will make sure that everything goes well right from the first speaker itself. So thank you very much. I'd like to thank all the speakers, including our Honorable Vice Chancellor, sir, and the panelists from the academic side of Dayanand Sagar University, as well as our industry partners who have taken our time and have been with us through to guide the students on this wonderful opportunity of career opportunities in specialized engineering programs. We look forward to seeing you in the first week of August. We are looking forward to as a 6th August as the date. We will communicate through Unigage the entire details to all of you, and we hope to have a very good interactive sessions with all of you. With this, we take your permission and we would like to log out of the session. Thank you so much once again. Have a wonderful day ahead. Thank you.